Today we are going to discuss the motion of charged particle in combined electric and magnetic field. In the last class we have discussed the motion of a charged particle in a magnetic field, and also we have discussed motion of a charged particle in an electric field only. Now today we are going to discuss the motion of a charged particle when there is an electric and magnetic field both, that is in a region in which electric and magnetic fields. If a charged particle moves, then what will the result we are going to discuss. That is motion of charged particle in combined electric and magnetic field. Now first we are going to discuss the velocity selector. As the name velocity selector, it will select a particular velocity. That means velocity selector is a setup to select charged particles of a particular velocity from a beam. Beam means the number of particles, number of charged particles with different velocities. Clear? Now velocity selector is a setup to select charged particles of a particular velocity from a beam passed through a space having mutually perpendicular electric and magnetic fields, which is called the cross field. If there is a region in which mutually perpendicular electric and magnetic field exists, then that field is called cross field. Cross field means there is an electric field and magnetic both, but two are mutually perpendicular. Now let us suppose there is a region, here is the region in which there is two fields. One is electric field and another is magnetic field. Let us say this is the direction of electric field, it is on the board, and in this region there is a magnetic field also, and the direction of magnetic field is it is perpendicular to the board and also perpendicularly into the board. Clear? Let us say there is a magnetic field which is perpendicular into the board, and there is a magnetic field which is which direction of which is on the board, and it is from left to right. Now if there is a charged particle passed through this region, then what happens? Let a charged particle having charge q enters a region with a velocity. Enter this region, that is enter a region with velocity v, and in this region there is mutually perpendicular electric field E and magnetic field B. The force on the charged particle due to the electric field, if V is equal to Q into E, and it will be along the electric field, right? And the force acting on the charged particle due to the magnetic field, force acting on the charged particle due to the magnetic field B is Fm is equal to Q into V cross B. And the direction of this field, what will be the direction? Right? What will be the direction? Let us say the particle is moving along this direction. Then V cross B, the particle is moving along this direction. That is the force on the particle that is force on the charged particle due to the magnetic field, is along the direction of what? Along the direction of B cross B. Now V is along this direction, B is along this direction. Therefore B cross B will be along this direction. That is, the force on the charged particle due to the magnetic field will be opposite to the electric field. This will be the direction of magnetic force on the charged particle, and this will be the direction of electric field on the charged particle, and these two are in opposite direction. Right? Now this is the magnitude of electric field is QE and magnitude of magnetic field is QVB, because V and B both are perpendicular. Therefore VB sin 90 degree. Therefore QVB is the magnetic force and this is the electric force. And we have already derived that these two forces are in opposite direction. That is, the force on the charged particle due to the electric field and force on the charged particle due to the magnetic field are in opposite directions. Clear? And their magnitudes are this. Now you can adjust E and B. Adjust E and B in such a way that Fe is FM. Is it clear? Now values of E and B are so adjusted that Fe and Fm, that is electric force and magnetic force, become equal and opposite, so that total force on the charged particle will be 0. Electric force is in this direction, magnetic force is in this direction. Therefore, these are in opposite direction, and now if these two are same, magnitude is same, then the net force acting on the charged particle is 0. If QE is QVB, then net force acting on the charged particle is 0. Clear? And in that case, V is equal to E by B. This is the condition, or this condition can be used to select the charged particles of a particular velocity out of a beam containing charges moving with different speeds. See here, the velocity. Now there is a number of particles is moving from this direction to this direction with different velocities. Clear? The particle, those which have the velocity V is equal to E by V, experiences no force. The particle with velocity V is equal to E by V experience no force. Then these particles will be moving in the undeflected path. The particle will not deflect due to the electric and magnetic field. And the particle with velocity not equal to this E by B will experience a force, and that will deflect it, and that force will deflect its path. Is it clear? There is a number of particles flowing this with different velocities. The particle which have velocity this experience no force. The force acting on the particle with velocity this is 0. If velocity, if force is 0, therefore it will move with its original path. Clear? And if the particles, those have velocity other than this amount, experience a force, and that will deflect its path. The crossed E and B fields therefore serve as a velocity selector. Only particles with speed E by B pass undeflected through the region of Thomson, first employed by the J.J. Thomson in 1897 to find or to measure the charge to mass ratio, that is E/M of an electron. This principle is also used in the mass spectrometer. Mass spectrometer is a device that separates the charged particles, usually ions, according to their charge to mass ratio. The charge to mass ratio is defined, then it will go in different path.